Good morning, guys. Welcome back from spring break first, and welcome to our last unit, Unit 10. We're going to talk about volume in Unit 10. So in the last unit, Unit 9, we talked about area. So area under a curve, area between two curves, and so forth. And now what we're going to do is we're going to take those areas and make them volume. So I want to start off just by kind of showing you a visual online so you can kind of just get a visual of what we're going to do before I start talking about actually how to do it. So if you use the link that's in the Word document or the PDF that you guys have to print off, it's right there on the screen, the GeoGebra one. I'm going to go ahead and go to that as well. Maybe. There we go. So what you're going to do is you're going to see here, we're just going to look at the left-hand side for right now. We'll look over at the right side. So if you want, just go ahead and uncheck this show end disk. That way you're not getting confused by what's on the left-hand side. What we're looking at right here on the left-hand side is the function 2 square root of x. Okay, so we see that this function right here, this gray function, this is our 2 square root x. And these rectangles would be what we would use if we found the area under that curve. So if you remember back when we first started area under the curve, we did L rams, R rams, M rams, and then we even did the trapezoidal rule. And we talked about, you know, if we wanted to find from the number 1, so if my lower limit is 1 and my upper limit is 9, so that's what these numbers are, from 1 to 9, because if you change this, you're going to see now it's at 4 to 9. So we'll just leave it at 1 to 9 just for the visual purposes. If I wanted to get a better area, I could increase the number of rectangles. So if you take this N slide bar and you slide it bigger, you're noticing you're getting a lot more rectangles, which is going to give you a better area under that curve. Okay, so in the last unit what we did is we found these areas using an integral, because an integral is going to make this n infinite, which is going to get us the best area that we can possibly get, the most accurate. Okay, so that's all that this little n is doing. So we don't really need it on 50 for now, just so we can get a picture. So I'm just going to go ahead and leave it on 6. Okay, now to find the area of this object, essentially we just did the integral from 1 to 9 for this problem of our function, the top function minus the bottom function. So remember, if it was in terms of x, then we would use a top function and a bottom function, but if it was in terms of y, we had to use a right function minus a left function. So here the top function would be 2 square root of x, and the bottom function would be 0, because that's where y would equal 0 on the x-axis. So here we just found the distance from this function down to this function. So essentially what we were doing, this black one, is we were finding the radius, okay, from here to here, or the height. Okay, so we'll call it, for an area, we'll just call it a height. But when we start looking at volume, we're going to actually be calling it a radius. So that just meant we had a dx. So this distance we called dx, the distance of our rectangle, and the height of our rectangle was the top function minus the bottom function. Okay, that is where we got the top minus bottom times dx at the end of our integral. Okay, so what we're going to do now is we're going to take these rectangles and we need to make it from an area to a volume. So to go from area to volume, area is 2 dimensions, volume is 3 dimensions. That means we have to add another dimension to our problems. So you'll notice over on the right hand side, this red line, this is where we're saying we're going to revolve all these rectangles that we've created to find our area around this. So we're going to rotate it. So if I move this blue one that says slide me, you're going to notice it's taking each one of those rectangles and it's revolving it around the x-axis. Okay, so if we go back over and do show end dis now, we're going to see the object that we get. We're going to get a three-dimensional object that kind of looks like a cone. Okay, the reason this side here is flat is because we didn't go all the way to 0. Remember, we're starting at 1 and going to 9. Okay, now if I want to get a better graph of this, then all I would need to do is increase the number of ends. So as we do an integral, we know we're increasing and we're getting the best. So now we're going to notice we're getting a much smoother shape. Okay, well, the question is, how are we going to calculate this volume? Well, volume, okay, is just our area, but then it's rotated. So that means if you look at each one of these these are called a cross section. So if I cut just this one rectangle out that I rotated and I laid it flat, you would see that I have a disc. This is why this is called the disc method. If I laid that out, I would have a disc, and the radius of each disc is the height to the function. Okay, so it is the height of the top function minus the bottom function. So if I'm trying to find the area of this circle, I need the area formula for a circle. Okay, so it's kind of more like a can turned sideways, like. So it's really going to be the area squared times pi, so pi r squared. So we're going to see how that plays in, but that's going to give us the area of each one individually, and when we take the integral of all of them with respect to dx, it's going to give me every single one of them to find this area. Okay, so let's go back to the notes page, okay, and we'll talk through what this looks like. Okay, so it says, give me just 1 second, I'm going to turn a light on and see if, yeah, that's a little bit better. Okay, so this one here says, let's look at just one cross section. So if we took just any one cross section in here and we had it rotated around, when we laid it out flat, we would get this shape right here. Okay, it's just a circle. Okay, so we know that the radius of this would be whatever from, because here we're rotating around the x-axis, so that's where it's 0 to the function itself that we rotated. Okay, so our radius of the cross section is just going to be our top function minus the bottom function. Okay, so that's our radius. So if I wanted to find just this surface area, so just the area of this surface here, okay, because area is just a 2 dimension, so that's a length and a width. Okay, so that means we're going to have sorry, my mind just went blank. Pi r squared. Okay, so pi r squared is our area formula, but we just said we knew what the radius was. Okay, so that means I can really say that this is pi top minus bottom squared. Okay, so that's just giving us this top, just the surface area up here. Then what we want to do is now we want to find the volume. So we want every single cross section of our function. Okay, so that means we're going to have to account for the width of each one of these, which is our dx, and then we have to account for every single one of them. So if you remember, we said that if we did an integral, that would take our rectangles and make it an infinitely many rectangles. So what this is going to look like is it's going to look like pi, because pi is just a number. Then I've got my integrand, so the integral from a to b of our radius, top minus bottom, squared, and then times the height, or the width I could say, of each one of those rectangles. So that's my third dimension getting in there from that area. Okay, so that's what makes it the volume, along with doing each single one using the integral. Okay, so this is the formula that we're going to be using, that one that I just wrote. So I'm going to rewrite it here just so we make sure, and it's highlighted on my paper, so if you print in color, then that helps. So pi times the integral from a to b, okay, of the top function minus the bottom function squared dx. Now, please make sure you understand a couple things. This is as long as we are rotating it horizontally. That means rotating it this way. So around some y value. So like the x-axis is y equals 0. Okay, so we have to see this horizontal rotation, not a vertical rotation. So we're not rotating it this way, we're rotating it this way. Okay, because yes, that is going to give us a difference. That means that these lower and upper limit, the variable in each of our functions, and the variable in this d at the end, all must be x's. So everything here must be in terms of x, because we're going to take it with respect to x. Okay, so that's just kind of giving us an idea of what this is and the equation that it came from. Okay, so let's look at the first example. I think I can get through the first example before I have to change videos. It says set up and evaluate the integral that gives the volume of the solid formed by revolving the described region about the x-axis. So first off, we're going to revolve it around the x-axis, so that's good. Okay, so that means we need to draw ourselves a little picture that has these criteria. Okay, so I'm just going to give myself a little sketch over here. Hello, little sketch. And I'm only going to do quadrant 1, so I'm really only concerned with this quadrant right here. Alright, so this graph, when I graph it, so 4 minus x squared, so if you plug that into your calculator, it's going to be a quadratic that opens down, that has that y-intercept up here at 4. So this is a 4. Okay, that means down here it's going to go through at 2. So this is going to look like this. Okay, so that's this function, y equals 4 minus x squared, that's that. Y equals 0, so y equals 0 is this right here. So I'm looking at this part. And x equals 0 is this. So basically I'm bounding it by the x and the y axis. Okay, so we're going to take this area that we just found, and we actually want to find the volume of it when we rotate it around the x-axis. Okay, so that means essentially we're going to get something that looks like this. Rotate it around, and then it's going to have this 3D object. So it's going to be a semicircle, if you can kind of get the picture of that. Okay, I am going to run out of time, so let me go ahead and stop here. I'll pick this up in the next video. Okay.